It's my pleasure to have Rohan and Sola here. So Rohan Biwalkar is a mechanical engineer at the Pittsburgh Technician. His specialty is computational fluid dynamic modeling and simulations, and also some engineering and internal combustion engineer. And Dr. Sola Talabi is the principal of Pittsburgh Technician, and he got his PhD from the University of Carnegie Mellon University. And today they will show us the experience on development and the demonstration of a test program to assess advanced reactor safety features and a case study on the integral pressurized water reactor. Let's welcome Rohan and Sola.
Thank you very much, June. So I think we'll have Rohan share his screen for the presentation. And while Rohan is doing that, I'll just get started by saying, first of all, thank you very much, June. Thank you to University of Wisconsin for inviting us today. It's really a pleasure and it's an honor on our part to be able to speak with you and talk to you about and share some of our research with you. I had been to Wisconsin about, I guess, a year and a half ago now, just before the pandemic, and I'd presented on some of our related research relative to nuclear construction issues based on my prior experience working on the Westinghouse AP1000 project. And when I was there, I got to meet a lot of the faculty. I was welcomed well. I spent some time with Professor Corradini, and it was really a very good experience. And so we hope to, in the future, maybe collaborate with Wisconsin on projects. And so this is a chance for you to get to know us a little better, also get to know our work. And so as we present here, again, one of the objectives here is to see how we can maybe work together in the future also. So the title of the presentation is Development and Demonstration of a Test Program to Assess Advanced Reactor Safety Features, a study on integrated pressurized water reactors. This is research that was sponsored by the U.S. Department of Energy Nuclear Energy Program. Next slide, please. So a little bit about Pittsburgh Technical. We're a nuclear engineering firm focused on safety and risk management for nuclear facilities. We have folks on the team with prior utility expertise, so folks who've actually worked at nuclear power plants. We have folks like myself who have prior experience working at vendors such as Westinghouse. And we also have an element of academic rigor that we bring to our projects, where we tend to collaborate with universities. As we said, we have proposals that we put in with Wisconsin, Missouri, Carnegie Mellon University, University of Pittsburgh, etc. Next slide, please. So for the project that we're going to present on, and the effort really has some significant context to it that we want to sort of lay the ground and explain the context for the research. One of the things we like to say is that we never want to do work that just sits on a shelf. So a lot of the research we do is driven by industry need, industry demand. And the industry demand here for this project that we're going to talk about is an ongoing effort to right size the concept of emergency planning zones for advanced reactors and small modular reactors. So as you may know, the Nuclear Regulatory Commission currently mandates 2 emergency planning zones. One is called the plume exposure pathway, which is a 10-mile radius, approximately a radius, so to speak, around each reactor site. And what the EPZ is it's the area where you need to have predefined and established actions in response to a potential accident. Some of the actions that can be taken within the area is, whether or not you shelter in place, whether you evacuate people, having potassium iodide provided to inhabitants of the area, having special training for emergency facilities that are in the area, etc. So there's a significant cost actually associated with having an emergency planning zone. And it's one that is necessary, but it should be risk informed. And the size should really be based on the risk profile of the plant. And so you don't need it to be any bigger, and you really don't want it to be smaller than it should be. And so it should really be informed based on the actual risk. So it really doesn't make sense for a 1,000 megawatt plant and a 50 megawatt plant to have the same emergency planning zone size. But the way the regulations are currently written, it's one size fits all. And so there's certainly a need to right size the emergency planning zones for advanced reactors and small modular reactors to make them more competitive. Next slide. So again, the context of this is within the potential deployment of a particular type of advanced reactor or small modular reactor, which is the integrated pressurized water reactor. And I know that I'm sure that folks in the audience who are familiar with the risks that are posed by a potential nuclear accident, which is the release of fission products. But one of the objectives of the containment vessel in a nuclear reactor is to again ensure that in the event of an accident, those radionuclide particles that are aerosolized are contained. So small modular reactors, and especially the IPWRs, have certain features that support the retention of fission product through natural occurring phenomena. And one of the ways that we are able to demonstrate a different risk profile for these small modular reactors is to try to quantify the potential increase in retention capacity of these reactor types in the event of an accident, fusion product. And so that's really what the objective of the study is to look very closely at this reactor type, integrated pressurized water reactors, and quantify the higher potential for retention, or as it's called, decontamination. Next slide. So the research was supported both by the Electric Power Research Institute and the Department of Energy. As we've stated, the motivation is to support right size of emergency planning zones by quantifying passive decontamination factors associated with IPWR containment vessels. And some of the critical factors here are the fact that there's a higher surface area to free volume, that the ratio of the surface area to free volume is significantly higher. And so per volume, there's more depositional surface that these IPWRs have than large light water reactors have, even though they're significantly smaller, but the ratio of the surface area to free volume is significantly higher. Next slide. So in terms of some of the significant benefits and impact here, so some of the available methodologies that we have and the available data, a lot of what we have is based on large light water reactor technology, and as we'll show in a subsequent slide, these don't really scale appropriately. And in terms of the impacts and benefits, as stated, the cost of maintaining an emergency planning zone is significantly high. And so to support the development and deployment of these reactors, we really have to sort of sharpen our pencils in terms of safety analysis and make sure that we're in various areas characterizing safety margin and ensuring that we're not being overly conservative to a point that it makes it too expensive to deploy the reactors. And so there is certainly an economic imperative here to support the development of and deployment of these reactors by ensuring that the actual risk profiles are understood and that the safety requirements are match up with the expected risk profiles. Next slide. So we've sort of stated the objective, and so just to explain the approach at a high level, to quantify the risk profile here, without going into too much detail, at the end of the day, it's really a question of understanding how much potential fission product is released from a reactor in the event of an accident and how far it travels. So it's the dose at distance relationship that we're really trying to understand. And based on that, the EPZ emergency planning zone is sized based on that expected dose at distance. And so just notionally looking at the chart here, prior to this work, if we try to quantify the dose at distance, we would have the red line, and the effects or the approach is really to try to characterize a green line based on the actual risk profile that the plant has. So the red line is a sort of the sort of one size fits all analysis that was done back in about 40 years ago with NUREG 0369. You can look it up, and so there's a characteristic dose at distance relationship for all plants in the US. But what we're saying here is that if we characterize the IPWR specific dose at distance relationship, we'll expect that we'll come up with something that looks more like a green line. And then based on that, we can size what the appropriate emergency planning zone should be with these reactors. Next slide. So as I mentioned, that one of the critical parameters is the relative surface area to free volume ratio. And based on that relationship, that relationship directly ties to the expected decontamination potential that a reactor has. And so currently, the data that we have is for large light water reactors, because that's all we've ever had in operation. And so we understand the relationship that we see in the lower left corner between large light water reactor surface area to volume ratio and expected aerosol decontamination factors, okay, because there's a direct relationship between those. But what we're trying to characterize is what we have is the regime in the upper right corner for integrated pressurized water reactors. And that's where the focus of the study was. And you can also say, again, even though this is just notional, that we can't extrapolate from the large light water reactors to get to IPWRs there, because there's the discontinuities here, and that it's not an SMR, not a scaled down version of the large light water reactor. It's a fundamentally different system. And one of the ways I try to explain to folks about this is it's as though a large light water reactor is a tractor trailer and an SMR is a motorcycle. And so a motorcycle doesn't have 18 small wheels. And so you can't really scale down from a large light water reactor to really understand the expected risk profile of a SMR. You really have to do a bottoms up estimation of what the risk profile is. Hence, you need to have an empirical studies, empirically developed data to really characterize the risk profile. Next slide. And so, so to sort of summarize the series of studies that we did to characterize the risk profile, the first was a feasibility study, which was an assessment to quantify IPWR decontamination factors. That study was done by Sandia, Sandia National Labs. And again, that was sort of, the objective of that study was to identify the appropriate theoretical models, theoretical constructs that would be required for further analysis. And also to identify the applicable depositional phenomena that would be affected by IPWR specific characteristics. Then in phase 2, we came in at that point because we're just a little less expensive than Sandia, but also fortunately we had a team that could also do the work. Because one of the challenges, as I'll explain later on, is that there was a very tight schedule and very tight budget to get this work done. And we were able to come in and help out. So we quantified the IPWR specific decontamination factors. And by the way, the decontamination factors, it's the sort of the figure of merit that is used in safety analysis to quantify the expected rate of depletion of the concentration, of the release concentration in the fission product in the reactor over time. And these reports that you see here are publicly available because this is DOE sponsored research. I know not all EPRI reports are publicly available, but these ones are. And so if you want to find out more about the test plan development, the CFD model development work that was done, you can look up in these reports. And so we developed the test plan, we performed a series of experiments, and we also developed a CFD model, which was verified and validated based on the data. And then in phase 3, we took the work from phase 2 and improved it by further characterizing and reducing some of the uncertainties, the methodology and results from the phase 2 work. And that's also available. Publicly available. Next slide. Next slide. Okay. Now, so I think in the interest of time, we kind of touched on this a bit. So let's go to the next slide. So, we wanted, for this presentation, we really wanted to talk about some of the specific challenges. So we talked about the background, sort of the what and the what, the why, and the how. And so now we want to talk about the challenges, the sort of the unique elements here. And we thought this topic may be interesting to you as researchers, because this is some of the, as you know, research projects are never straightforward, and there are always some specific challenges, especially with data acquisition, setup, limited resources, etc. And so we wanted to share with you some of the challenges that we had and how we tackled some of those challenges. So the first is the fact that we really had, as I explained, limited opportunity to scale from available large light water reactor data. And also the stakeholders had requested that they wanted us to have one-to-one scaling for our applications, because there've been some challenges with scaling, and as you may know, to some extent, it's science and art when it comes to scaling. And so one of the objectives was for us to try to limit any scaling that we did on the study. And so we had to test at actual post-accident thermohydraulic conditions, so relatively high temperature and pressure, and also a one-to-one scale geometrically for the critical parameters, as we said, was one of the critical parameters was relative surface area to the positional surface area to free volume for the reactor. Also, we had to have a relatively quick turnaround because the regulatory effort had already commenced. And this was, as you may be familiar with, the new scale application for a reduced EPZ. There was a topical that was released a few years ago, and that work had already started prior to this study being commissioned. And so we were actually trying to have the data catch up with the regulatory process that had already commenced. And so we had a relatively short schedule, about 2 years to get this done. Again, limited budget because it was sort of an after the fact or an afterthought, so to speak, in that there was the realization of the need for IPWR specific data sort of came a little late. And so that folks had to sort of scramble and get a budget together, which was limited. But so we had a short window of time, limited budget. And also we had to, because this is significant work, there were NQA1 requirements for the execution of the experiments, development of records, etc. How we tackled the challenges, one, because we had to do a one-to-one scale geometrically, we actually had to design, conceptualize, design, and build a test vessel, a containment vessel to emulate actual accident conditions and acquire the data geometrically on a one-to-one scale. So the test vessel you see is relatively large, but it has the ratio of the positional surface area to volume ratio that's characteristic of the SMRs. And so it's an ASME certified IPWR containment vessel. We designed, fabricated, and commissioned it in Pittsburgh. Again, it's designed specifically for nuclear accident simulation. The overall schedule took 30 months for engineering, procurement, construction, and testing. So the entire program was completed from start to finish in about 30 months. And that included testing, the data acquisition, report writing. Next slide. So one of the challenges also was to improve our data acquisition. Prior to this work, the prior art, so to speak, had used coupons, the coupon method to develop the expected rate of depletion of the fission product in the containment vessel. And so essentially, as we had stated, the objective here is really to quantify how effective the containment vessel is in decontaminating, self-decontaminating, or reducing the amount of fission product in the volume. And so prior studies had what they would do is pressurize a vessel with the fission product simulant and periodically take out coupons over time, and based on the concentration of the coupon, you can develop your depletion curve. As you can imagine, that's an invasive process, and it's sort of error prone, as one might expect. And so we use the PIV, particle image velocimetry, and our understanding is that this was a first of a kind application for this specific type of work, given actual post-accident conditions. So next slide. So the video you see shows the, well, we have the setup there. Can you pause it for a second first, and let's explain the setup. So for the PIV, essentially what we do is we shoot a high intensity laser into the vessel, and we take pictures over the depletion period. And so there's a high speed camera. What you're seeing is you're seeing the laser setup, and you're seeing the high speed camera that's they're both looking through viewports. There's a viewport where the laser shoots in where the laser shoots into the instrument vessel, and there's a viewport where we take pictures. And so you're looking at both the camera and the laser here, and we're able to characterize the rate at which the pressurized aerosol within the vessel is depleted over time. So it's really the change in concentration over time. And so pictures start with a high concentration over time. It gets depleted, and based on that, we can develop a depletion curve. So the images that we get from the PIV are then post-processed to estimate particle concentration in the CV. Next slide. So also we have improved data acquisition by the use of various sensors for temperature, pressure, and humidity. So it's thermocouples fitted into thermal wells in the vessel, various pressure gauges, transducers, humidity sensors. And again, the reason we need to get all this thermohydraulic data is the phenomena of interest, which include phoretic processes like diffusiophoresis, thermophoresis, are very much dependent on the thermohydraulic conditions. So in the case of thermophoresis, it's phoretic transport based on the thermal gradient, and diffusiophoresis is based on a steam concentration gradient. And so we needed to have the data acquisition methods and equipment to measure all the applicable conditions within the vessel. And what you're seeing here is a cross section of the vessel showing the thermal walls, and in there is where the thermocouples go. Other special vessel design features, some measurement of the thermal hydraulic parameters and particle concentration. So The vessel has relatively smooth internal walls with a 32 RA finish to reduce effects of surface roughness and which could affect the flow and measurement. Also, it's stainless steel to prevent corrosion. You can imagine the size of the particles that we're measuring are really those within the respirable range, so within 1 to 10 microns. And so the vessel itself has to be very clean. We want to make sure that we're not, tracking or measuring anything other than what we put in. And so we can't afford to have any kind of dust, any kind of crud, any kind of foreign material. Hence, it's stainless steel and very, very clean vessel. So again, designed to withstand the PWR accident pressure of 200 psi and temperatures of 500 up to 500 Fahrenheit. There are viewports included for the PIV laser measurements, as mentioned. Sampling ports included, along with high pressure sampling valve for optional external particle analysis. So for calibration of the PIV system, we actually also did the coupon method to independently ensure that the concentrations measured by the PIV correlated with those that we took by direct sampling. So that's sort of how we checked the PIV. Also, simulation of real-world IPWR deployment scenarios. So one of the requirements also was that, as you may know, some of the IPWRs, such as the new scale IPWR, is designed to be immersed in water. And so that obviously affects creates potential condensation on the containment vessel walls, which drives the diffuse theoretic velocity of particles. And so we wanted to be able to emulate that condition and also emulate dry conditions, because some of the IPWRs are in dry environments, but also we wanted to be able to understand the effects of going from an immersed condition to a dry condition over the transient. And so the containment vessel that we have has an outer jacket that can be pressurized with water to emulate conditions of being immersed in water. Also, because the studies are parametric, because we're trying to really understand relationships, so all the critical parameters had to be varied. So varied temperature, varied pressure, varied the geometric conditions, including the relative surface area to volume ratio. And so the way we did that was by changing the free volume inside the containment vessel by putting larger, basically reactor vessel cylinders. So we have a cylinder that represents the presence of the reactor vessel. And so by changing the size of those, we can essentially change the relative surface area to volume ratio. That's also one of the unique aspects of this study, is that we're able to vary these parameters. So what you see here are the various inserts that we put into the containment vessel to emulate the presence of the different sized reactors within the same containment vessel. And so this kind of shows you basically just how we do that by having various reactor vessel sizes. We change the surface area to volume ratio, and we capture a range of 0.6 to 0.75 per foot. some of the additional design features, demonstration of phenomena common to containments with high surface area to volume ratios, including natural convection cooling, characterization of steam concentration and containment based on rates of pressurization and condensation, characterization of accident progression rates related to containment vessel pressurization, simulation of high and low containment pressure environments to study variation of aerosol deposition rates with pressure. Some of the other experimental equipment that we have include steam generators that are used to obviously generate and pump steam into the vessel. We have an electric immersion heater that represents the heat generated from the reactor vessel, and then other equipment to develop the appropriate thermohydraulic conditions, including air compressors, etc. One important aspect is obviously the simulant that we use to represent the fusion product, and so we use nickel, and there are a couple of reasons why we did this. First, the reactor vessel, first, the input that we got from the IPWR vendors included that the reactor vessel material largely consists of steel, and so the difference between IPWRs and large light water reactors, as you may know, is that the containment is for the IPWRs is stainless steel liner, while for the large light water reactors you have concrete and you have significant debris, etc. And so your inventory for large light water reactors includes concrete, includes debris, which makes your aerosol, your final aerosolized particles relatively lighter. So it's not just the metals coming from the reactor, you have all the additional debris that's in your agglomerate. So the agglomerate for the stainless, for the IPWRs is essentially just what comes out of the reactor. So it's generally a little heavier. And so we needed to characterize a relatively different aerosol from what had been used in prior experiments in terms of density, in terms of the characteristics of the aerosol, hygroscopicity, potential to retain water, etc. And so based on our research, nickel particles were the best option. And also we certainly needed particles that would be sensitive to the data acquisition method, PIV. And so we have this well documented as to why we picked nickel. It does have some sensitivities with handling nickel in the lab, but it turned out to be a relatively good similar. This is just a PNID of the setup we have. You see the various the containment vessel here. That's a reactor simulant in there. Various data acquisition equipment, thermocouples, etc. We have the computer that's hooked up to the PIV system that does the data processing, and we have the rest of the system here to maintain and regulate the thermohydraulic conditions, etc. Also, a lot of safety-related features here, rupture discs, etc., for blowdown. Safety features. Next slide. And that's just again an overview of the lab. Some of the Pittsburgh technical staff, and in this picture we have folks from the NRC and DOE who had come down to sort of kick the tires on the and some Carnegie Mellon University faculty also, and even some folks from NewScale who had come down to kick the tires on the system and observe some of the experiments in progress. I also wanted to touch on quality assurance. As stated, because this is safety significant work, we had to meet certain NK1 type requirements here. So there's went with what's called a graded approach for the quality assurance. And again, this is also documented where we had to establish critical parameters. Those had to be tracked. Critical equipment had to be calibrated. The materials test and equipment was controlled and maintained. And these records are all stored. I believe they have to be stored for about 10 years. And so, again, all the QA requirements to support this type of safety-related work were done. At this point, I'll hand it over to Rohan to do the hard part. So thank you, Rohan. Go ahead.
Yeah, thank you, Sola. So moving on to the experimental data that we collected throughout this study, there were several critical parameters that we varied. It was a parametric study because obviously in order to characterize the effect of all these parameters on aerosol deposition, you need a parametric study within a certain range in order to make your conclusions. And the parameters that we varied were the reactor vessel temperature, the containment vessel wall temperature, and the initial bulk gas temperature, which was always taken to be equal to the reactor vessel temperature. Then we varied the steam concentration at the start of the postulated or simulated accident. When we say 0, it essentially means that the conditions throughout the containment vessel are dry, while for wet conditions to study the effect of diffusophoresis, the mass fraction was 0.7. We also varied the initial pressure and, as Sola explained earlier, the area to volume ratio. A total of 15 test cases were executed, and each experiment was repeated twice, meaning 3 experimental test cases per 15, per case, basically, were executed for a total of 45. So first off, we had to understand what the baseline cases are for sedimentation or gravitational settling for thermophoresis and diffusophoresis. The parameters are shown in this figure for the RV, CV, and the bulk gas temperatures. Then you have the pressure and the steam concentration. The area to volume ratio for all baseline cases was 0.67 per foot. And these were the common baseline case parameters. And in case of the case-specific parameters for gravitational settling, the CV wall temperature was equal to the RV wall temperature, and there is no steam. When we study thermophoresis, that is movement of particles in the direction of a thermal gradient, we have a temperature of 220 Fahrenheit on the CV wall as opposed to 500 Fahrenheit on the RV wall. So there is a thermal gradient and there is still no steam. And in order to study diffusophoresis, there is a thermal gradient as well as a steam concentration gradient, which is the result of steam condensation on the cooler CV wall as compared to the hotter RV wall. And thus different baseline cases allowed us to study different deposition mechanisms. So in this video, you can see this is what the output, this is the output that we received from the PIV laser system. And as Sola mentioned, it captures images, and the post-processing involves like the intensity of particles. Based on that, the particle concentration is determined. So over here is a set of around 1200 images, 2400 images that were post-processed over a period of 80 minutes. And we saw particle concentration, the equivalent of particle concentration as a decay curve, an exponential decay curve. And that is how for all experiments results were developed. One of the most important findings of the study was that convective flow, which is a result of the thermal gradient between the CV wall and the RV wall, as well as the buoyancy of the bulk gas, This was identified as a significant decontamination mechanism. So as you can see near the RV wall, the bulk gas is going to rise because it's hot. Near the CV wall, which is relatively cooler, bulk gas is going to descend, and that sets up this circular convective flow. In the phase 1 study, diffusophoresis, thermophoresis, and gravitational settling or sedimentation had been identified as key phenomena, key deposition mechanisms. But in phase 2, we also identified a fourth one, that was convective flow. And that is extremely important because it sets up when there is a thermal gradient, and it results in the fluid flow or movement of the bulk gas, which in turn pushes particles to deposition surfaces. This is also significant because it's not been credited for particle deposition in Gen 3 plus design applications, and it contributes significantly towards particle transport. And of course, it was only observed in case of thermophoresis and diffusophoresis for those baseline cases and others, because in case of gravitational settling, there is no temperature difference between the RV and CV walls. So these are the results that we received for the baseline cases. As you can see, gravitational settling is slowest. These curves were, by the way, achieved by smoothing the data smoothing all of this data that we received from post-processing of the PIV laser output. So for the thermophoresis baseline case, also referred to as TGC, which stands for thermophoresis, gravitational settling, and convective flow, the deposition is significantly faster than that of gravitational settling, but in the presence of steam, it is the fastest. So this agrees with the physics of the problem, with the theory that in the presence of steam, you also have diffusophoresis, therefore your deposition is going to be enhanced. And based on all the theory that we had studied during the phase 1 project, the phase 2 experimental data was in agreement with the theory. So some results from the parametric study that we executed, as you can see, varying the RV wall temperature, so that reduces the magnitude of the thermal gradient between the RV and CV wall, and it ends up affecting the particle deposition. As you can see, as the temperature of the RV wall increases, the deposition rates are faster. Similarly, when the area to volume ratio is increased, that is to say, when the inner reactor vessel becomes like it has a higher radius, when you increase that radius, you're increasing the area to volume ratio because the containment vessel radius is constant, and that results in faster deposition as well. This is because the convective flow does not have as much of a radial distance to traverse as it does when the area to volume ratio is smaller. And that's why with an increasing AV ratio, we saw increasing particle deposition rates as well. Also, presence of steam enhanced particle deposition, as we saw from the previous slide. And with an increase in pressure, the same was seen because at higher pressure, steam condensation rates are higher. And that results in faster diffusophoresis. So, of course, in order to compare with what results we have from prior studies, as we can see, the characteristic case, that is an average of all the data which was received for the entire parametric range. So for a RV wall temperature of 400 to 500 Fahrenheit, for a range of 20 to 200 PSI pressure, and for an AV ratio of 0.6 to 0.75. In this entire range, after averaging the data and performing statistical analysis on it, we found that the decontamination factor was 19.3, which is comparable to an LLWR with a containment spray. And that in itself is a fairly significant finding because it shows that IPWRs have the potential of faster decontamination than LLWRs. So little more on the statistical analysis. We found that at time of 69.16 minutes, there was a 95% confidence level that 95% of the particle decontamination had taken place, and that decontamination factor at that particular time was 19.3. So, of course, as we mentioned earlier, CFD modeling was performed throughout this phase as well in order to support experimental findings and execute simulations for thermal, hydraulic, and geometric parameters that were beyond the range of experimental data collection. We developed this predictive CFD model in the commercial code Converge through the use of user-defined functions. And we have submodels for steam condensation, particle transport, which was coupled with the bulk gas flow using a drift flux model, as well as particle deposition. So we found convective flow in the CFD model as well, as you can see from the figure. And we also found that CFD simulation showed good agreement with experimental data, and the decontamination results for AV ratios beyond the experimental range were also obtained, and they agreed with the overall qualitative trend. But CFD simulations are extremely computationally expensive. Just to put things in perspective, 2 minutes of CFD simulation time was equivalent to 12 days of real time. So that is just 10 seconds per day of simulation. So it was that slow. And that is why we had to develop a methodology to extrapolate some of the CFD results using the experimental data. So the technical conclusions from this phase 2 research, the most significant findings are that the IPWR DF, the average DF under consideration, is comparable to an LLWR DF with a containment spray. We found that convective flow is a strong particle transport and deposition mechanism, and that the particle deposition rates increase with an increasing RV wall and initial bulk gas temperatures, increasing AV ratio, increasing pressure, and also in the presence of steam. Plus, we found that the CFD model showed good agreement with experimental data, but it was computationally expensive. And just touching upon the research that was carried out beyond phase 3, a lot of recommendations to investigate some additional phenomena were made at the end of phase 2 by our stakeholders. And that's why we embarked upon this additional research for characterizing some more phenomena like particle resuspension, agglomeration, and deposition by impaction, also the effect of pressure fluctuations, and some other conditions as well, like what if there is a thermal gradient on the CV wall? And what if the CV top surface or the containment vessel top surface was uninsulated? So in phase 2, the top surface is insulated, but what if that were absent? Also characterizing the effect of the presence of large particles which have a diameter beyond 10 micron, which was the range in which we had simulated and experimented upon particles during phase 2. And also the effect of a non-uniform initial particle distribution. So a homogeneous particle distribution was assumed for the CFD simulations as well as for the experiments. And this phase, part of the research was to investigate what if the initial particle distribution is not homogeneous. And we characterize these phenomena through experiments as well as some modeling. So experimentally, we characterized resuspension, agglomeration, and studied our phase 2 data in order to understand the effect of pressure fluctuations. And based on for the modeling, since the CFD model was computationally expensive, we developed a more simplistic code, a V&V code in Python for faster simulations. And of course, since we had a lot of insights from the CFD simulations, it made a lot of sense to use those while developing this new code for faster calculations. Like the insights that we used were the stratification of the CV volume into different zones where different phenomena are in effect. So for instance, the dew point temperature plane is very significant because only between the dew point temperature and the CV wall is there a steam concentration gradient, because and that is where diffusophoresis is going to take place. And throughout the containment vessel, between the reactor vessel wall and the dew point temperature plane, there will be a very negligible steam concentration gradient. So diffusophoresis will not be active there. And also we found through CFD that the thermal gradients near the RV and CV walls were steeper than those throughout the containment. Of course, existence of convective flow was a key finding, as was the evaluation of particle deposition velocities throughout the CV volume. So all these calculations are not made just next to the CV wall where most of the deposition or where a significant amount of the deposition takes place. They are made throughout the containment vessel volume. And this code was validated against experimental data and also used to characterize the effect of additional phenomena and conditions on aerosol deposition. So through modeling, we also characterized impaction. We characterized the effect of the initial particle distribution by studying some heterogeneous particle distributions. And we also studied the effect of the thermal gradient on the CV wall. So this was studied due to some stakeholder feedback, where we were asked to investigate some scenarios in which the IPWR is not fully submerged, but rather partially submerged. This may be a result of the way it was set up, deployed, or it may be a result of the sink in which it is submerged losing that amount of water due to an accident. And also, what if it is not submerged at all? What if the deployment is in a dry environment? So simulate that as well. And also the effect of the uninsulated vessel top surface was characterized. And in order to study gravitational agglomeration and the effect of large particles on agglomeration, a standalone new code was developed, which was even more simplistic than this V&V code used to characterize the other phenomena. So experimentally, we characterized resuspension, agglomeration, and studied the phase 2 results, experimental data for pressure fluctuations. Resuspension, we found that it occurs in the presence of a thermal gradient. As you can see here, this happens late in the deposition phase in the absence of steam, where beyond 63, like beyond an hour at least, at 63 minutes, 67 minutes, and 70 minutes, you see a slight increase in concentration in some cases. And what experimentally we were trying to find was when this occurs. So we found that it occurs in the presence of a thermal gradient, is unaffected by pressure, and does not occur in the presence of steam. So this supports the theory that resuspension is highly dependent on convective flow, because convective flow is what occurs during the presence of a thermal gradient between the RV and CV walls. For agglomeration, we did not find any evidence of experimental evidence of agglomeration during the post-accident deposition phase, because theoretically most of the agglomeration takes place before the deposition phase. And through our pressure fluctuations, through our study of the phase 2 data, we found that if pressure increases during the deposition phase, steam condensation is enhanced, and if pressure reduces, steam condensation rates are also reduced, and they both directly affect particle deposition. Using the phase 3 V&V code, we found that for agglomeration, using the standalone code at least, it was found that gravitational agglomeration has a very negligible effect on particle deposition. As far as impaction was concerned, we found that a particle bounce, we studied impaction through the characterization of the effect of particle bounce, like rather than assuming that if the particle hits the wall, it deposits immediately. And using this probability of particle bounce, we were able to characterize impaction. We found that it increases with an increase in steam concentration, but this model does not take into consideration the effects of surface adhesion, which will result in more changes. The effect of initial particle distribution was studied with a heterogeneous distribution where particles were skewed towards the top half of the vessel, the top region of the vessel, and we found that it does cause differences between the overall decay curve and the decay curve in case of a homogeneous distribution assumption. For the CV thermal gradient, we found that as the CV submergence depth increases, particle deposition rates are enhanced, which makes sense with the theory, because increasing the depth means activation of diffusophoresis due to steam condensation on the CV wall in those regions. We found that if the vessel top surface is uninsulated, it does not affect the particle deposition significantly. And as for large particles, it does not enhance gravitational agglomeration. This is probably due to large particles just dropping off very quickly. If your particle radius is higher than 10 microns, they don't take much time to just drop off from the top of the containment volume to straight onto the bottom surface. So conclusions from phase 3, we received a lot of insights into the phenomena that were modeled, additional phenomena that were modeled and characterized. We received insights into how each of these phenomena affect aerosol deposition. We found that the modeling of resuspension is critical since it is driven by thermal gradient, which drives the convective flow. And as for uncertainties in the experimental data, we found that they were due to the measurement devices, since all the experimental data was collected with all phenomena being in effect. Finally, varying IPWR submergence depth and the heterogeneous initial particle distribution, they are both potential real-world scenarios which have to be characterized through either modeling or collection of experimental data in order to really study and understand their effects on aerosol distribution. And with that, I would like to hand it back to Sola for the final slide. Thank you.
Thank you, Rohan. So we presented we started with presenting the overall objective of characterizing the risk profile for IPWRs, and we've we explain the different phases, the phase 1, phase 2, and phase 3 work, how we developed the theoretical models, how we verified and validated them experimentally, the results. We provided a comparison of the results of the decontamination factor that we get for IPWRs with just passive safety or passive mechanisms to a large light water reactor with active mechanisms such as sprays. So that sort of tells us that an IPWR without any active mechanisms, just using passive decontamination mechanisms, can be as effective as a large light water reactor with active mechanisms such as sprays. The importance of that is that, so if you're looking at, say, a Fukushima type event where the active mechanisms such as your pumps were rendered useless because of the tsunami, what this is telling us is that IPWRs have features, passive features that don't necessarily require those active systems, and so it makes it more resilient. It's more you don't need a human being to actuate something for your passive features passive safety features to be implemented, which is very important for SMRs. So in summary, also regarding the process and the experimental work, we provided a first-of-a-kind experimental containment vessel that we conceptualized, designed, fabricated, tested to perform this work. There were several technical challenges that we encountered and disposition, such as the high temperature and pressure environment, data acquisition challenges, the no scaling objectives, having one-to-one geometric and thermohydraulic conditions, the relatively quick turnaround to support the regulatory effort and the budget that we had to work with. Some of the future work that we want to do, and here's maybe the future ongoing conversations that we'd like to have with the University of Wisconsin is we're looking to see how we can repurpose the vessel to support advanced reactor fission product transport and deposition studies in general. Because when we think about it, even though it was designed for IPWRs, at the end of the day, it's really a containment vessel that can withstand relatively high temperatures and pressure, and has viewports that can really help us interrogate what happens over the depletion period. And so it can be repurposed to fit thermohydraulic and geometric conditions of other reactor types. And certainly it's, again, because it's a DOE funded facility, we would like to see it continue to be used even beyond IPWRs and current needs. And with that, we'll take any questions that you may have.
Yeah, so do we have questions from the audience? It's a little over time, so we might have 2 quick questions. So if not, Sola can ask you a question.
Hello, June. I'm not sure if you were asking a question, but I couldn't hear you.
Okay. So so now most of your work are focused on the light water reactor. So what's your plan? I mean, for the future demand from advanced reactor, how you adjust your facility to meet the very different demand from different advanced reactor designs?
Yeah, so it's a good, very, very good question. So we've worked with microreactor vendors And there's some potential application there, but even for HCGRs also. But the vessel would have to be reconfigured somewhat to support the geometry and thermohydraulic conditions that are specific to those other reactor types. So as you know, the facility was designed specifically for IPWRs. But I think with some scaling and with some adjustments, we can reconfigure and do other emulate conditions for other reactors.
Yeah, okay, thank you. So do we have other questions from the audience? So if not, let's thanks again for Sola and Rohan for this very impressive presentation. Thank you very much. So hope everyone have a great day.
Thank you very much for having us. It's a pleasure.
Thank you.